We're nearly there. Welcome back, everyone. As promised, though, we're only going to start at 6 o'clock sharp. And looks like we can start. Welcome back, folks. We're going to be finishing off week 4 before we know it. We'll come back on tomorrow's class and have our first exam review for exam 1. And it's going to only go through these particular 5 different sections. So today we'll be finishing up all the content that can possibly appear on the very first exam. But just to keep in pace with the schedule, we'll be moving into Unit 3C today as well. We may not finish it, but either way, this unit is not going to be on the next exam. There'll be some good ideas here thinking about percent scientific notation, which will be helpful nonetheless. But this will be officially the exam 2 content we'll be working on today as well. Well, the big announcement again is all about the exam, it looks like. We'll be reviewing tomorrow's class. I mentioned I was going to put together some more review problems, but I'm getting a little bit short on time, and this is a pretty big problem set on its own. Probably what I'll do after calling for questions from everyone in the class is select particular questions from this longer document that looks like they'll be helpful for their exam review. But any questions at the moment, folks, about the exam or otherwise? Okay, well, as far as the announcements are going, we have our quiz number 2, which is going to have its first official due date tomorrow. And the new quiz 3 was posted either today or yesterday. The week is kind of running together. Some people have already completed this, so good on you for getting through those. I'm trying to grade these quizzes as soon as possible, just so that you have that feedback as you get into exam number 1. And if you, say, missed any of the due dates on these quizzes, I'll still accept them for full credit if you get them into me, say, by the end of the course. But that would be the very first thing you ought to do in preparing for the exam is make sure you're caught up on all work. The quiz 3's official due date is February 12th, which is in line with our pattern on due dates, a 1-week turnaround. But if you solve this quiz early and get it sent in to me, say, even late on Sunday night this weekend, I should be able to get that graded and sent back to you before the exam on Monday. Other ways you can get your score improved if you missed a due date is in the homework system itself in Access Pearson. This is what it looks like if something's gone past due. We're finally at that point where that's occurred. It says here on my course home, this should be about what you see. This is the so-called student view. It could be slightly different, but it lists out the calendar dates and a listing of the sections, due dates relative to those sections. And it says I have 1 past due assignment, but that isn't quite right. It's possibly because I worked on an assignment and then just left it, the very first unit 2A. So if you feel like something's missing here, click on the entire course to date. I think that's a lot more helpful, the tab, to find everything. If you click on this, it reveals the 2A, and I guess it probably didn't show up on the last list because I started it and then left it behind. And this is the one I haven't started at all, 2B. These are all completely open. So even if you got, say, 99.89% on a unit, and you felt like you wanted to go back to just get exactly 100%, you could do that on any section whatsoever. But you might have to click on this to reveal everything that's in there. So click on, say, this one here. You can go to review and practice just for new, fresh problems to study for the exam. But if you're trying to improve your score, definitely click on this button. And any question you want to revisit, say this one we have partial credit on, just click on the problem. Gives us a new navigation pane. We're back in the assignment. And let's see here. I want to continue working on this one, get a new shot on it, improve the score on that particular question 5. Just click on similar question, and it'll give you a fresh one to run through. Sometimes it's kind of annoying if a question has multiple parts, because if we make a mistake on, say, the middle, and then we got through the whole problem, you get partial credit. So if you want 100%, unfortunately, you have to restart the whole question from top to bottom. That's probably the most annoying thing about it. But it's kind of nice that you're never going to be fully penalized. It can take time to get back to every question and get through them. But as you're studying for the exam, that would be a good time to go back and see some of these old problem sets. Well, those were the major announcements I want to discuss today, in particular, just looking at that homework system again to show where things are. Any last questions or comments at all, folks, before we go back to 3B? Okay, let's get started. Oh, maybe one other small announcement is you should get in the habit of checking your grades just regularly to see if everything is in there correctly, see how you're doing in the course, not just in this course, but all of your courses. And I'm pretty much every time I get a new thing turned in, I'm going to be putting in that grade right away. As far as the MyLab through this link right here, what I'm doing is sometimes at the start of the week, maybe if I have time in the middle of the week, but definitely right around Friday or so, I'm going inside that system and I'm pulling an Excel sheet of all the scores. Your grade for MyLab here is just an average on all the sections that have gone past the due date, the same dates I'm listing here. So if your grade looks slightly different because maybe you started a new section, but you're not quite through with it, that would be the reason. I'm only showing your grades on the sections that are past the due date. But if you have any questions in particular about your grade, never hesitate to ask. I'll be happy to help out. But here's where we left off in Unit 3B. We talked about this problem a little bit the last couple minutes before class ended, but so now we can return to it and finish it. The refresher is when we say a joule, or capital J for short, we're talking about the standard unit of energy in the SI system of units. And we have a couple interesting scenarios that gives you an idea of what a joule really means. It's the amount of energy, or could be measured in the amount of work you would do to lift about 100 grams, say an apple, roughly 3 meters, about over your head perhaps. That would be 1 joule of energy doing that amount of work. And this is more a scientific way to view it. It's the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So joules are very important. If we're talking about energy released, we have a couple ways to get energy that we're going to compare against. 1 kilogram of coal being burned releases 3 times 10 to the power 7 joules of energy. And if we release the energy through nuclear fusion of 1 kilogram of hydrogen, the specific types of hydrogen, we get 6.4 times 10 to the power 14 joules. And the kind of idea with this problem, in the context of putting numbers in perspective, is scientific notation is precise to reveal orders of magnitude, but sometimes it's hard to get a good feel for just how impactful 10 power 14 is as compared to the order of magnitude 10 to the power 7. So the instructions on this one says, compare the energy released by fission of 1 kilogram of hydrogen to that released of burning 1 kilogram of coal. It's kind of a vague open question when it says compare energies like that, but one standard thing you could do is divide the quantities. If we take, say, the larger value, divide by this quantity, energy released through burning of coal, we can say this energy released through fusion is X many times as that energy released there through coal. So here's a standard way to compare. Go 6.4 times 10 to the power 14 divided by 3.0 times 10 to the power 7. The analysis on this is first, do the divisions of this part here before the powers of 10. So we can, oh, hang on, and also make sure to copy this in right. That's 10 power 14, meaning to be the larger value, not 10 power 4. So in the calculator, do the division of the integer part here, or do 6.4 divided by 3.0. We're going to write this also in scientific notation, rounded to 1 decimal place. So we'll keep a 2.1 for that division. So this becomes 2.1 times, and as far as this goes, we're just subtracting the exponents, power 14, subtract power 7. And if you ever forget that exponent law, you know there's always going to be a calculator available to you on the exam. There's no harm going 10 power 14 divide by 10 power 7, just to make sure we're on the right track. Notice this calculator does not give it in scientific notation, so that'd be 1, 2, 3, 4, 5, 6, 7 to get our value. So we get 10 power 7 altogether, and now we have it in scientific notation. So that's the whole comparison, but it really leaves a lot desired in what we just did. So a good way to put down what this number means is we can say the energy released actually, let's put it down below. That might fit a little bit better. The energy released from fusion of hydrogen is 10 to the power 7 times greater than, and I should be specific, this will be 1 kilogram of hydrogen burning 1 kilogram of coal. And that's quite a lot. If we say 10 power 7, oh, here's the calculator again. 10 power 7 is telling us that's 10 million times the amount of energy for the same amount of mass. 1 kilogram of coal versus the 1 kilogram of hydrogen. Well, that's the rundown on that. For the instructions as stated, when it just says compare the energy, if this is all you had, the result of the computation, you know that qualifies. If I needed this part right here, the instructions would have to say very specifically, give an interpretation of your answer using the context. And I'm not going to throw a lot of questions out that beyond what we've already been doing in the notes. So there's not going to be a sudden question shift on instructions versus what you've already seen going on a section by section basis. So think of this as just us thinking about the number, making sure it makes sense. Well, any last questions or comments at all, folks? Finishing these section notes. Okay, and by the way, if you're curious about this, you've probably heard of, oh, hang on, that's a typo here. This wasn't fission. Fission is splitting atoms apart. This was meant to be fusion. This is combining the atoms, fusing them. Sorry for that weird typo right there. That number is not going to be accurate unless we say fusion both times. That was a weird typo. But you've probably heard of nuclear fusion potentially in a science class, maybe in high school and so on. People have been talking about it for decades, really. And finally, really, these reactors are being built. It's getting to the point where it's no longer a scientific fiction, something that's putting down in theoretical physics. They're building these reactors as to right now, and it's all now about a matter of making them for scale. So they are really going to be used like other nuclear reactors, which use fission. Well, we're now done with this section notes. We're going to go on to the new material, 3C. So this is the part of the notes that are going to be again on exam 2. There's still some great information here that we'll be going over and being really careful with. And we'll mention any tie-in where this is content that looks like it'll be part of exam 1. So for example, if percents come up, if scientific notation comes up, we'll mention that. But these specific kinds of questions, and with those wordings, these will be on exam 2. Well, this section is kind of tricky in a certain sense. Significant digits on its own is an interesting concept. It does work together with scientific notation, but it is kind of its own thing at the same time. And the idea is we're talking about precision of numbers when we're thinking of significant digits. Precision is the amount of detail in a measurement, whether you're measuring something to, say, heights to the nearest inch, or maybe you're measuring heights to the nearest 1/8 of an inch, we'd be talking about precision. And now if we make a whole lot of scientific measurements to a certain level of precision, do any kind of arithmetic on those numbers, say like multiplying them, dividing them, or multiplying things in scientific notation, we need to convey the accuracy of our number by including the precision in that number as well. In other words, we have to be very careful of significant digits, or else we can miscommunicate that the number we have is more precise than it really is. So for example, if we're saying take something like 53.5 inches, let's write that in Desmos. We make a measurement, 53.5 inches, and I'm not sure what the context is, but let's say we divide by 17.3 inches. You know, there's a certain level of precision on both of the numbers. They're only accurate to the nearest tenth. And if we would go to report an answer with this many significant digits, all these values, we might have miscommunicated to our audience that we knew the original numbers to that level of precision when we really didn't. Mathematically, this number is entirely correct. But when we think about making measurements in the real world and including the uncertainty, the fact that we only have so much precision when we go to measure something, this is where significant digits starts to become very, very important. And again, it's a tricky concept, so we'll go through these ideas very carefully. First, let's look into the summary page. This is probably a page that we'll pick up and use quite a bit as we go through the notes. So as far as significant digits goes, it tells us non-zero digits are always considered significant no matter what. With that in mind, let's do example 1 right now. For example 1, we'll state the number of significant digits. That'll be like one part of the answer in my lab. And then we'll say what the implied precision is for the given number. So we're going for 2 values on this one. How many significant digits do we see when that number is stated? And the second value, how precise is that number really? Well, to start, it tells us if we see a number, all the non-zero digits of that number are going to be considered always significant. And there is 1, 2, 3, 4, 5 non-zero numbers. So this tells us right away that this has 5 significant digits. Then returning to the precision side of this computation, it's asking, well, the precision is defined to be the amount of detail in measurement. So when we look into this one, we have a number that's to 0.12. 2 is in the hundredths place, so we can say this is the precision is nearest. Let me backtrack, not 10th. We're in the hundredths place where the red dot is, so the nearest 100. Well, any questions at all, folks, getting through that concept there? Okay, it absolutely gets pretty tricky. These are one of those kinds of problems where this is a very good table to come back to and be really careful when we look into significant digits. Now in part B, we go 0.003, and let's see what this second line says. Zeros that follow a non-zero digit and lie to the right of a decimal point are always significant. That's not our case. Our zeros are to the left, not to the right. Zeros between integers, like sandwiched between non-zero integers, they're always significant. So this would have 4 significant digits, this one would have 3, but still not our context. We're in this situation for the current problem. It says zeros left of the first non-zero digit, that would be 3 on this one, as in 0.006 or 0.00052, are never significant. So the significant digits on this number starts right here. Actually, let me just highlight these to convey all 5 on that one. That means this number only has 1 significant digit. Does that make sense to folks on this number here? Okay, so back to this example, this one would have had, one significant digit. The leading zeros are not significant. And this one would have just two significant digits. The leading zeros, again, non-significant. Even though it only has one significant digit, notice it's extremely precise. This one is to the nearest tens, hundreds, thousands. So for precision, we have a measurement to the nearest thousands. Well, let's keep on going. Any questions or comments so far? Okay, again, these are pretty tricky, so let's analyze this one together as a class. I'll give us just a few moments to think about this one. Think about the number of significant digits using the table above and the precision. Okay, anyone happen to have number of significant digits on this one?
Is it 2?
Absolutely, good call. Let's see if we can cite the direct information for that. It says zeros to the right of the last non-zero digit, but before the decimal point, such as in these two cases, are not significant unless we say so right away. Yeah, absolutely, Brianna. Two significant digits on this one. So this one has two significant digits, but maybe we made a measurement and it just happened by pure chance to be exactly 350,000 and 000 years. If that was the case and our precision was really to the 1 year, it would have been six significant digits, but we would have to tell people. We couldn't just give this number without indicating that there is more significant digits than you would see visually. So without further information on this one, it's exactly two significant digits. To me, this one's pretty tricky. Here, we ignore the significant digits to the left. Here, we ignore the significant digits to the right. And a number like this, where there's zeros in the middle, we also ignore those. That would have two significant digits. And this one would have two as well. So this one is two significant digits. And does anyone see the precision on this number if it's just two significant digits?
Is it the nearest hundred thousands?
Close, not
Is
exactly
it the
100.
nearest, I mean, sorry, is it tens?
Yeah, it would be the nearest 10,000s, absolutely. So when that first non-zero digit occurs, moving to the left, that's going to be the precision on this one. 10,000 years is our nearest measurement. So we'll say here, precision. This one's going to be to the nearest 10,000 years. So far, pretty tricky on these. Any questions at all, folks? Thinking of either three so far? Okay, there's more, so let's give the next two a try. That table is really vital, so we'll just use it as a temporary screenshot as we run through the notes. So here it is again. Might as well make it bigger. Hang on, Microsoft Word is fighting with me on that. There we go. Okay, so with the problems we've done so far and the notes below, let's try this out again. Here again, this gets kind of tricky. I see a 4502. And I think I might have misstated something here earlier when we were looking at this one. When we see the 4002 or the 306, these are zeros being sandwiched between non-zero digits, and those kind of zeros would always be considered significant. So this one would have 4 significant, and this one would have 3 significant digits. Again, I think I misspoke when I was looking at those just a few moments ago. Sorry about the confusion on that. So looking into this number right here, even though there's a 0, we don't just automatically say they're not part of the significant digits. If this was 4, 5, 0, 0, 0, 0, 0, 2, and so on, all of those zeros would be significant. So this one would have altogether 4 significant digits. Let me see if I can spell that right. There we go. So 4 significant digits on this one. Again, this one sometimes informally is good to think of as being the sandwich rule. Zeros sandwiched between non-zero quantities will always be significant no matter what. And the precision on this one is not anything we've done too differently. We just have to be careful with that place value. And there's a really great place value table in the e-text as well. That's good to have a reference. Counting these carefully, we're at the tens, hundreds, thousands, 10,000s, 100,000s. So this is to the, in precision, nearest millionth of a meter. So precision, nearest millionth of a meter. And notice at that point, it starts to get convenient to just state that in terms of scientific notation. So you could say in other words, to the nearest 10 power 6 of a meter for the nearest million. Either way would be a fine way to state it. My lab usually has like options that you select, multiple choice. So that's why I'm writing it out more often in this kind of way. And this one's really tricky as far as precision goes. But anyone see what the number of significant digits should be on this number here? Oh, sorry, missed the chat. It wouldn't be 6 on this one. Yeah, this one would come out to as 4 significant digits, exactly. The scientific notation is definitely a bit of a distraction, and more so if you're thinking about the precision of the number. But let's write down, this one is 4 significant digits, and precision. Probably the best way to think about the precision on this one is just unpack the scientific notation on it. This number, 2.123 times 10 power 12, would be equal to 2.123. So we have an order of magnitude 12 on this one. So I'm going to need altogether, here's 3 places. We need to come up with 12 of them. So here's 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's our number. Let's double check. Going from the right where the decimal point is, 3, 6, 9, 10, 11, 12 is where we would land to get the 2.123 in scientific notation. So the precision on this one is very, very blunt, not precise at all. This is in miles, so maybe this has something to do with, say, measuring distances in the universe. And let's count this off again. Recall also 10 power 12 reminds us of trillions. 1, 2, 3, 4, 5, 6. So here on this decimal place, we're talking millions. Now we're in billions. And this would be the trillionth place. So here's hundreds, 100,000. Here we would have 100 million. And right here is in the billions. So this precision would be to the nearest billion mile, or 10 to the power 9 miles. Well, any questions at all on either one of these problems so far, folks? Okay, so pretty extreme numbers we're looking at with a significant digits. And again, all these measurements, if we did anything with them, maybe combine data at various levels of precision, we want to keep in mind the significant digits and when we report the answer. And that's what the next portion is all about. We're going to carry out the computations. There's no context in these problems so far, but we'll look into context on the later on problems. We'll do the operations and give the answer with this specified number of significant digits for the sake of practice. And these are pretty tricky, so we need to go pretty careful as we go. That table is still of great value. Starts off not too bad. We need to carry out the operation, so we would just break out a fast computation device. Don't forget your calculator on the exam. 386.04 times 43.002 gives us a number of this form, 16,600.4928,208. Let's put that down just for the sake of showing the steps on this one. And let me double check the digits on that. Oh, I knew I forgot a number, 49.49208. So if we were just doing an ordinary mathematical problem, that's a great answer. It's exactly dead on the right value for the multiplication. But if we were doing scientific measurements and we're reporting values, maybe in some kind of report in a journal that people are going to read later, this would imply that we have a number with accuracy 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 significant digits altogether. But we really don't have that level of precision altogether. We're going for 5 significant digits on this because the numbers themselves have 5 significant digits, and that's a pretty good rule. If one of them had, say, 4 significant digits, that should be the reported value on the number that we'll get. We're not going to focus too much on those kinds of rules just yet, more so on just practicing the concept of significant digits itself. So if we want 5 significant digits, this is way too many. And the idea is we're going to start moving from the right to the left, round if necessary, to report the actual significant digits in our answer. Or excuse me, to give an answer with the specified value number of significant digits. So this would be 1, 2, 3, 4, 5 significant digits altogether, which would mean to 5 significant digits, we would report this multiplication is equal to 16,600. And we should pause on that. Recall that if this problem didn't have any context, say the thing on the left was just not there, and you saw that number, that would be much like, say, this number, where it would have 1 significant digit, or that number, where it would have just 2 significant digits. So the context on this is really important, and it wouldn't be a bad idea to say, just in a parenthesis or additional statement, this is to 5 significant digits. So that number there was really precise to the nearest tenth in what we reported. We're thinking of these as always significant. And that's what was stated here. The zeros that we put in our answer are not significant unless stated otherwise. We knew it was 5 significant digits, but it's good to just really hammer that in because it seems to contradict what we did in just the last problems. Does that make sense to folks on why this one is still 5 significant? Okay, let's try out another one. And this almost looks like multiplication. Let me see if I can just fix my formatting here. Okay, that looks like an actual decimal point. To my eye, it almost looked like we're still multiplying those numbers together. Okay, just double checking that value. And same game on this one. This time we're dividing, and we want the answer to just 3 significant digits. So start off by taking 54,320, divide by 12. We get this number. Let me just write it down to several decimal places. 4526.6 repeating, it looks like. You can put a bar on that if you like, or you could put in just say several sixes, that'd be fine. Or sometimes to say repeating, people go ... to say 6 is thereafter. So either way you'd like to say it, I'll go with the bar method, which seems more routine for repeating decimal. That's the exact value of 54,320 divided by 12. But now if we want 3 significant digits, anyone see what the number would be that we must report? Yeah, sorry, I missed that chat there, Echo. This is saying that all 5 are significant digits on this particular problem right here. Well, anyone see what this number should be?
Would it be 4,520?
You're very close, and there's kind of a judgment call on it, right? We want to go to 3 significant digits, but once we get there, we have to round on this one. So it's like a surprise out of nowhere. This one would round up when we report it in significant digits. So this would be 4530 altogether to now 3 significant digits. Again, that's pretty tricky. So if we were going 3 significant digits, this would tell us round up. So that's, again, kind of out of the blue on this one when this comes up. Any questions so far, folks, on either A or B? Okay, let's see. We've got a couple more to go through. Looks like its scientific notation is the major idea with these next ones. Oh, that's not going to work. Let me undo this. Let's keep on moving this table as we go. Oh, if I can find a way to do it. Maybe I'll leave that one there as it is. And here's the next couple parts. So this time we're dealing with scientific notation at the same exact time, going for a specific number of significant digits. And at the same time, we want to represent our answer back in scientific notation once we have it. And so this one is to 4 significant digits. So is this number here. So giving an answer to 4 significant digits would make sense. That's telling us essentially the number of precision in both of these numbers. That's not quite right. The precision would be different because the order of magnitudes are different. But if we have values accurate to 4 significant digits and we do the multiplication, that's the value we'd want in the answer. So first, to start out, we could take the 7.345 times 8.424. And if you put in your calculator times 10 power 5 times 10 power 2, there's no harm done in that either. But sometimes it's just easy to combine these to 10 power 7. If we want an ultimate answer in scientific notation, that'll save us a step. So first, the multiplication of those two numbers gives us the 61.87428. Then multiplying 10 power 5 against 10 power 2, here we're adding the exponents and getting times 10 to the power 7 altogether. That's our scientific notation we've been practicing all along. And now all we need is 4 significant digits. So we start moving from the right. That would be 1, 2, 3, 4 significant digits altogether. We also have to round at the same time. But for this value here, the 4, this would tell us to round down, or that's just going to be removed. So instead of rounding up, we're rounding down this time. I don't think the arrow would make more. Well, let's leave it there. So this becomes 61.84, 61.87 rather. Now we have the 4 significant digits. And with the scientific notation, this will be times 10 power 7. So when the scientific notation part comes up, really this is all it is. A pretty good review problem on scientific notation, but also combining writing the answer with significant digits all at once. Yeah, once you get good practice, it's not too bad, but any questions on this one?
I do. Doesn't scientific notion have to be between 1 and 10?
Oh, thanks for mentioning that. Yeah, I would have lost credit on this one, so good eye on spotting that. So let's also go a little bit further. Here's the good reminder for the exam setting as well. Not in scientific notation, because as you said, it's not between 1 and 10. It exceeds 10 by quite a bit at a 61 and some change. Not between 1 and 10. So again, thanks for spotting that. We will rewrite this as, let's move the decimal point 1 spot left. So now it's a 6.187. That produces another times 10 power 1, because we shrunk the size. We need to put this to make it bigger. But then it's times 10 power 7. So the ultimate answer on this one, a lot more steps than I was expecting, is 6.187 times 10 to the power of 8. Good eye on that one. Thanks for catching that error there. Does that make better sense to folks on that ultimate answer? Okay, again, this is something that becomes really important in the MyLab homework for an example. When this comes up and you feel like you've done everything right, that could be pretty frustrating. And it was just a matter of getting the number between 1 and 10. Let's try this out again. I think this is the last one of the set. This time we're dividing these numbers. I said 2 significant digits on this one for, it looks like kind of just a random request, I guess just for the sake of practice on it. So now in this division, we'll start by taking 3.48 divided by the 2.16. Oh, didn't mean to do that. Let me bring that back. We get this number, 1.6, looks like 1 repeating. So we can say 1.61 repeating times 10 to the power of negative 3 times 10 to the power of negative 7. Let's combine those on the next step. But also if we want just 2 significant digits, we'll start from the left and only capture the 1 and 6. With the 1 here, we're just rounding down to just a 1.6. So altogether, to 2 significant digits, it's 1.6 times 10 to the power. These add up, but it's going to be a negative 3 minus 7. So we're getting a negative 10 altogether. Very extremely small number with that order of magnitude. Well, any last questions, folks, on thinking about the significant digits problem?
Would you not add the negative? I don't know. I thought it would be -4, so I'm a little confused why it's -10.
Oh, gotcha. There's a couple ways to think about it. One way to think about 10 power negative 3 is it's really saying it's 1 over 10 to the power positive 3 altogether. Another way to get intuition on that is definitely the calculator is a big resource when it comes to these exponents. So 1 divided by 10 power 3 gives us 1,000th altogether. And same idea with the 10 power negative 7 on this one. This would give you times 1 over 10 power positive 7. And double checking what that looks like in the calculator, this would give us 1 over 10 power positive 7 will give us 1 times 10 power negative 7, getting us the same answer back. I think I did it backwards, how we did the last one. There we go. So that's really not too helpful, is it? I think this calculator is just at some point only going to give you scientific notation when they get this extreme. It works for power negative 3, but power negative 7, this is just 1 over 10 to the power positive 7 together. But now you could bring these both together and get 1 over 10 power 3 times 10 power 7 in that way, with the idea of just multiply across tops, multiply across the bottoms. And this is where it kind of eliminates the confusion. I mean, exponential notation with exponent laws are tricky enough, and they're worse with exponents that are negative. So if you can think in terms of the positive exponent problem, here it's more straightforward, right? We would add those exponents together to get 10 power positive 7. But then that would be, oh, let me try again. Power 3 plus power 7 would be 10 to the power 10 itself. If you brought that into the numerator, you get 10 power negative 10, wrapping back to that conclusion there. But well, once again, another thing you could do in the homework is, or in a calculator, is just multiply them together in any old calculator. It might not give you the scientific notation like this one is giving us, but it'll give you some good intuition if you convert your number you see in your calculator into that scientific notation. But does that help with that question there with the negative exponents?
Yes, thank you.
You bet. Thanks for asking about that one. Again, that's probably one of the things that's going to be maybe trickier about exam 1 is navigating the exponent laws whenever they occur. So just a fast roundup of things to have ready to go on that concept. Let's just write down a couple things that I would say would be a great addition to the notes that you would want to bring to on exam 1. So for the purpose of exam 1, exponent laws, keep a power m times a power n as a power m plus n. But the trickiness with this law right here is it'll work for any powers whatsoever, positive, negatives, decimal numbers, irrational numbers like square root of 2 or pi, that always come up in that format. The other one is a power of m divided by a power n would be a power n minus n, so you can subtract in that kind of way. It has 2 separate versions. So if you keep your answer in the denominator, you get a power n minus m instead. And the other one, kind of what happened with going from here to here, that's pretty confusing on its own, is a power negative n is 1 over a power positive n. So you can take something in a negative exponent, just throw it into a denominator to flip that power positive. And it also goes both ways, 1 over a power negative n. If you start with a negative exponent in the denominator, you could rewrite this with a positive exponent back into the numerator. So the big idea is if you flip positions, you're always flipping signs, or what these 2 laws are saying. Well, any other questions so far, folks, with any of these operations? Okay, I think this is the trickiest part of the notes, the significant digits and precision ideas. The next part of the notes is actually, although it's not on exam 1 material, this kind of stuff might look pretty familiar. These are ideas that we've seen before. So with the idea of just thinking in terms of exam 1 material, we were back in, say, unit 3A. Here's where we looked into this particular equation. we had the ideas of absolute change versus relative change. Here we're looking into absolute error versus relative error, and it came back again in unit 3B. You know, in a way that's kind of nice, even though it might feel slightly redundant, it was just a different context. In unit 3B, this one is also on the exam, we looked into somewhere on here, I promise. Or maybe not, maybe I forgot. For some reason, I thought there was a related topic on these notes. I think I misremembered on that one. So not on 3B, think just 3A rather. Unit 3A just really connects very directly with Unit 3C. So even though it's on exam 2, this is pretty much an exam review problem on its own. The difference is the idea of a new value versus reference value. Here we're thinking in terms of the measured value minus a true value. So keeping the color coding identical, just for the sake of really our sanity at this point, we want to keep these the same. So here in the absolute change formula, carrying that down, we're going to think of the measured value playing the same role as the new value in the unit 3A. When we talk about reference value, we're thinking about the true value, the value that should absolutely exist, the true temperature of an object, the true height of a person, the true mass of an object, and so on. And the only thing new when we go into relative error as opposed to absolute error is we're just talking about percentage. Don't know why that flipped colors all of a sudden. I have too many documents open, I guess. The numerator is the absolute error, so we keep these values the same, just like before. And we divide by the true value in this kind of way. So one thing that's kind of cool about this book is it's designed to really kind of just build off these old ideas. And there's a strong degree of parallelism in just the formulas themselves, which is kind of pleasing. It helps us learn this material altogether. So think we're about to do these kinds of problems in Unit 3C, and we're just talking about error in measurement as well as the relative error in making a measurement. Any questions about the formula so far? Okay, so with this new landscape, here's what we're going to do in this situation. The idea is dealing with uncertainty, and if you're in any kind of context where you're making a scientific measurement, whether it's weight on a scale, height of a person, or so on, you always have to keep in mind that the precision, the accuracy, and error are parts of what you're dealing with in those computations, those measurements. It says from the instructions, find both the absolute and relative errors in the following situations. We're going to round to the nearest tenth if it's required in these problems. And here's a pretty near and dear scenario, something you can imagine happening to you, maybe a summer project. It says you're cutting a piece of lumber for a home improvement project. Maybe you're overhauling the bathroom and you're trying to widen it, so you need a support frame. You're cutting a piece of lumber. You looked into the plans and it says the board you need needs to be exactly 24 inches. Well, it says also you went to cut the board and there's error in the measuring tape. There's error in how we cut it with the saw. We've got to have a board that's 23.6 inches. This is going to be the measured value. This is kind of nice in a way that the context has to really direct you into what is what. And this is a really big giveaway. The measured value, we literally just said, we've measured it to be 23.6 inches. So that helps to identify as measured value. The board length is supposed to be 24 inches. And so even though it's not what we got, we think of the true value is what we required in the plans to make this work. So we're thinking of the 24 inches, not the actual length of the board, but it's going to be the true length that we require for this particular project. So this quantity will be the true length. And sometimes, again, it's easy to get kind of mixed up with those two values in the context. It's important because some formulas do put absolute values around those, but ours do not. We are treating the negative sign as an important direction as well. So flipping them could give us the wrong answer on this one. Does that make sense to folks on this being the measured length and 24 inches being the true length? Okay, after we've done that though, we're pretty much just reviewing what we did again in Unit 3A back in the day. When we did a problem like this, say we were looking at the context of the total student loan debt increased from 1.06 trillion to 1.57 trillion in the year 2020. We thought of that as the new value. And the analogous thing in this context is that's the measured value of 23.6 inches. Here, the 1.06 trillion, that was the reference value. And here, this is the reference value, the required length in the plans for the whatever project we're doing here. So we want both absolute and relative error. We can start by saying absolute error will be always specifically the measured value first minus the true value. So it'll be 23.6 inches minus the 24 inches. So we would have a value altogether, negative 0.4 inches. So our absolute error is we're short by just 0.4 inches to getting exactly what we require. At least that's what we've measured. It's plausible. We cut that board and it's just dead on. But when we took a measuring tape, remember the mantra, measure twice, cut once, but maybe we measured twice, we cut and we measured again just to see if we got to where we needed to be. Our measurement says we're short from the true value we have to be in, but there's error making the measurement itself. So we don't know exactly how much we're short by. This is just the absolute error in making the measurement itself. Now we're wondering what is the relative error in terms of a percentage in making the measurement of 23.6 inches. But nothing that we've haven't done before, we'll just say now relative error is going to be equal to, each time we did this in Unit 3A, you notice we duplicated the numerator and just divided by the reference value or the true value in these notes. But thinking in terms of the shortcut, you just take whatever you computed for absolute value, throw it in the numerator, and divide by true value. So it's not a bad idea to think in these terms. Take negative 0.4 inches, divide by the true value, 24.0 inches. The units are going to cancel off, and we're also converting it into a percentage at the same time. So times 100% here to actually give us the relative error we're looking for. And this will give us a good idea of just how much we're off by. Is this going to destroy the bathroom if we're doing an overhaul? If we have something like a 30% error, we're probably concerned. But if that percentage is small, we'll probably be just fine. Just maybe bang on it a little bit till it looks square and just right in the project. So looking into this, we have negative 0.4 divided by 24 in the calculator times 100. We're rounding to the nearest tenth, so this will be rounded to negative 1.7%. So if we measure 23.6 inches, the absolute errors were short 0.4 inches, but relative to what we tried to get, the true length, we are short by 1.7% of the 24 inches we required. Well, any questions at all, folks, with this kind of a refresher problem, really? Okay, let's try this out again. Let's capture this and bring it down just for quick reference. And here's the new context. So it says here, you're calibrating a synthesizer in a music technology lab. We're told the synthesizer itself, an expensive piece of hardware, is set to output a standard A note at 440 hertz. But you have another measurement to see, well, what does it come out as? A frequency counter measures the output of this synthesizer to be 432 hertz for the standard A note. Doesn't seem terribly off, 432 hertz. And we want to measure that in terms of the absolute error and the relative error. But again, the hardest thing about these kind of problems in my mind is to really determine what would be the measured error and what would be the measured value and what would be the true value. Sometimes it's easy to get mixed up on these, thinking about the context. Well, if we can nail down the measured value, we'll know what the true value is. Anyone happen to see in this new context what the measured value should be? Is it 440 or 432 hertz?
432.
Yeah, good call. And again, it's kind of confusing to me because this is a frequency counter, and I'm thinking of this as being a very high degree scientific equipment in music technology. It feels like that should be the true value, but it's not. It's really still just the measured value. And another way to think about this is the measured value is always something that happens with some kind of human intervention. You grabbed a device, whether it's a measuring tape, whether it's a frequency counter, any measurement that required human intervention that you made yourself is thought of as being the measured value. Let me fix that color coding really quickly. That's thought of as being the measured value. So does the synthesizer itself actually come out as 440 hertz? We don't know, but we're still thinking of that as being its absolute true value. That's the value it's supposed to be. That's what the specification is required. So we're thinking of that as the true value in this problem. But this is always a great giveaway. I'm going to write the problems the same way it was written in my lab as well, using that same kind of language. And if you see the buzzword measures, anywhere a measurement comes up is meant to be just directly that quantity. But again, sometimes it's easy to get them backwards in your head and just make a simple mistake. So we have measured output of 432 hertz. So now we're ready for the absolute error. Absolute error in this problem is 432 hertz, subtract the true value, the specifications of the synthesizer, its output that the output is set to, has a true value of 440 hertz. And the error on this one is going to be, looks like negative again, negative 8 hertz. That's possibly something you would hear. You might be able to tell the difference between the 430 hertz and the 432 hertz. And if we look into the relative error, they'll possibly give us another idea on this. All we're doing is dividing by the true value and converting it into a percentage. So another run through looks like this. Relative error is the prior value we just calculated, absolute, negative 8 hertz. So as a process, this is a great shortcut in just writing down the result. Divide by the true value, 440 hertz. Convert to a percentage. And you notice if you didn't write the units, really not a big deal because we expect them to cancel out when we convert this into a percentage. So the error between what the synthesizer is meant to output versus what we measured is, let's take a look, negative 8 divided by 440 times 100, that's to the nearest tenth, negative 1.8%. I don't know that I would be able to hear that, to be honest. I don't have enough of a head of the difference between these two hertz to even be sure if I would hear that or not. But I bet you there's a lot of people that will, and they'll probably get annoyed if things are off just right. If you paid big money to a ticket to hear some kind of sympathy and things are off, that's probably something you would notice. But any last questions, folks, on getting through part B? Okay, well, we just have one last topic to close out this unit. Thinking about measurements and uncertainty, we're going to delve into the definitions of accuracy versus precision. And this is one of those pairs of definitions that can absolutely make your head spin a little bit because they feel entirely synonymous. In ordinary language, when people are just talking amongst friends, they probably are using these words totally interchangeably to mean the same thing. But in terms of scientific measurement, they're not the same. We have to be very careful. They're going to be involved with relative error, like we just calculated up here. I shouldn't have scrolled down so far. Accuracy is going to tell us how close we are in terms of relative error. We'll say a measurement is accurate if it has the smallest possible relative error. So we're thinking in these terms once again. But precision we've defined before already when we were thinking in terms of significant digits. Precision describes the amount of detail in the measurement, whether you're measuring to, say, the nearest inch, the nearest tenth of an inch, and so on. We're talking precision. Whereas if anyone says accuracy, it's just relinking with the last concept. Accurate means small relative error. And it's pretty good work to spot the difference between them in the next scenarios. But these will be the topics that we will return to when we come back after our exam 1. So we'll finish off these notes on 11th February. But any last questions at all, folks, with what we've done today before we call it a night? Okay, well, thanks for your hard work today and participation. And thanks for your careful eyes on spotting these weird errors like these. They seem to be easy for me to slide right past my notice. Have a great night, folks, and we'll be back to next class reviewing for exam 1. So come prepared with questions. I'll probably be selecting questions out of version 2 once we're done with the student-directed ones. But have a great night. I'll see you all tomorrow.